Hey, so we're going to start talking about writing and graphing equations of lines. Algebra 1 stuff. So hopefully some review for you, and nothing that's going to be too difficult for you to pick back up. So there are the standards we're going to hit. And out of both sections, we're going to talk about writing and graphing equations of lines, and then we're going to talk about some theorems that deal with perpendicular lines in just a few minutes. Okay, so if we're going to write equations of lines, we've got a couple of options here. We've got standard form and slope-intercept form. Standard form looks like that, ax plus by equals c. You have to remember that if we're talking about graphing lines, we're representing points. Points have coordinates. Coordinates are x comma y. So your equation should have x's and y's in them, right? It should have an x and a y in them. So anyway, we remember that standard form is ax plus by equals c, where a and b are not 0. And the nice thing about standard form is it's easy to find x and y intercepts. If you remember, we use the cover-up method, right? The cover-up method basically says if we cover up the x part, solve for y, then we'll know where the line hits the y-axis. And if we cover up the y part and solve for x, then we'll know where the graph hits the x-axis. Okay, a, b, and c are just any real numbers. So, for example, something like 2x minus 4y equals 8 would be a standard form equation of a line. Okay. Anyway, where a, b, and c are just any real numbers. Okay. Slope-intercept form. If you remember, y equals mx plus b, where m is the slope and b is the y-intercept. This is the most commonly used form of the equation of a line. It's the easiest to use to graph. You've got where it hits the y-axis right there in front of you, and then from the y-axis how to move in terms of the slope. So it's used quite a lot. Here's the third form, if you remember, point-slope form, but we're not going to talk about that form very much, so we'll just move on. All right? Now, get into some examples here. If I want to write the equation of this line, and I want to do it in slope-intercept form, well, we math people aren't very creative, so we kind of tend to call things, name them using words that we need to have to do them. So in other words, slope-intercept form means we need to have the slope, and we need to have the y-intercept, right? The y-intercept is where it hits the y-axis. Well, this graph hits the y-axis right there. And since b is just a single numerical value that we're going to put into the equation, we just use the y value. So our y-intercept is 4. Okay? Now, the slope. We've got to find the slope. And we talked about last class that slope is rise over run, or it's the change in y over the change in x. The change is represented by subtraction. Right? So in other words, we've got to subtract the y's, subtract the x's. And so the y's are 4 and negative 2. So I can go 4 minus negative 2. And the x's are 0 and 3. So if I go 4 minus a negative 2, then I have to go 0 minus 3. Got to go the same way. So 4 minus a negative is plus, so 4 plus 2 is 6. 0 minus 3 is negative 3. So I'm going to leave this in fraction form as negative 2 over 1. Okay? So I've got my y-intercept. I have my slope. I'm ready to write this in slope-intercept form. I simply go y equals, and I'm going to put this in a different color so we can see it. So y equals negative 2 over 1 x plus 4. Or, if you'd like, you can certainly drop the fraction now and just make this y equals negative 2x plus 4 and be in fine shape there as well. Okay? But we want to remember this slope formula. We're going to use it again. Okay? And we're going to use it in a situation like this, where now instead of having a graph, I just know what point my line goes through. So I want to write the equation of a line that passes through this point and is parallel to this line. Well, as we said before, it would be helpful if we had a y-intercept and a slope to put it in slope-intercept form. Unfortunately, I don't have a y-intercept. I still need the slope. No matter what, we always need to know what the slope is. So what I know is that my line is parallel to this line. So what's the slope of this existing line? Well, hopefully you know that the slope is 2. Okay, that means the slope of my line is also going to be 2, since they're parallel. Okay, now, to get to the equation of a line, how would I have gotten the slope if I had known a couple of points that were on my line? Well, that's where that formula comes back in, right? So slope 2 had to come from the change in y over the change in x. Okay, now, I only have 1 point though. If you remember, you go back to this, we plugged in the 2 points into this whole thing right here. Oops. Right? Those were the 2 points. I only have 1 now. So I'm going to plug this point in for x1 and y1. I'm going to strategically place that. Okay? And it's just going to make my equation, my formula, easier to use. Right? So y1 is 1, x1 is -1. And so these guys down here in the denominator become plus. So I get 2 equals y2 minus 1 over x2 plus 1. Now, if I make my slope a fraction like I like to, slopes I think are always more helpful if they're fractions, then I get a proportion here that I can cross multiply and solve. Or at least cross multiply and work with. So when I multiply these, 1 times y2 minus 1 is just y2 minus 1. 2 times x2 plus 1 is I got to distribute that 2 here and here. So I go 2x2 plus 4. Now, I know that the equation of this line is just going to have a plain x and a plain y in it. So at this point, I'm just going to drop the 2 notation. And I'll just solve for y. Add 1, add 1. And so y equals 2x plus 5. And that's the equation of my line in slope-intercept form. And it came from knowing the slope and using the slope formula. And that's what we want to do here. Okay? All right, third example here. Write the equation of a perpendicular line. It's kind of the same process, only we've got to use what we know about perpendicular lines and their slopes. Right? So there's going to be a line that passes through J that goes through this point and is perpendicular to this line. And there's the equation. Well, the slope of this line is -2, which means that the slope of my line, so the slope of my, is going to be flip it and switch it, remember? It's the negative reciprocal. It's the opposite reciprocal. So we flip it over and make it a half. We change the sign, it becomes positive, so the slope of my line is 1/2. Now I'm going to do the same thing I did in the last example. How would I have gotten that slope? Well, I could have done the change in y over the change in x. I only have 1 point, so I'm going to plug this point in for x1, y1. It would work just fine if you plug that point in for x2, y2. It's just that the algebra gets a little bit more, I don't know, a little bit scarier maybe. So anyway, I'm going to plug in for x1 and y1. So I get y2 minus 3 and x2 minus 2. And now I'm going to cross multiply. So I get x2 minus 2, because that's 1 times x2 minus 2. And then I'm going to distribute that 2 and get 2y2 minus 6. At which point I'm going to drop the 2 notation. Add 6, because now I'm trying to solve for y. Divide by 2, everything. And so I get y equals 1/2 x plus 2. Okay? And so that's just using the idea of perpendicular lines and having that flip it, switch it slopes. Okay? So we're writing equations of lines. Okay? Now, what can lines tell us? Here is a graph that talks about the gym membership. It models the total cost of joining a gym. Write an equation of the line, okay? Now, we can kind of do this the same as before, only we have to have the slope. So we got to go find the slope ourselves. So subtract the y's, subtract the x's, and that gets you 363 minus 231 over 5 minus 2. Okay? Which this is going to be, what, 132 over 3. Okay? You can divide that out, actually, and you get 44. So the slope is 44. Well, to get the equation, I can use this formula again. So 44 is equal to, and just plug in one of the points now. And I'm going to plug in 5 and 2 because life is easier if I plug in smaller numbers, and those are my x's, so I can't do that. Never mind. I'm going to have to use one of the y's. So how about we just use 231. So now we'll go y2 minus 231 over x2 minus 2. Put that over 1. The 44, cross multiply. I get y minus 231. I'm just dropping the 2's now in my x and y. And I get 44x minus 88. Add 231 to both sides, and you get 44x plus, what is that? 112, 143. Okay, so there's the equation of that line. See? Told you. Now, question is, what are the meaning of the slope and the y-intercept? Okay? Well, look at the graph. Along the x-axis is your months, and the y-axis is cost in dollars. So as your months increase, the cost increases, you're paying a monthly fee. How much is that monthly fee? For 1 month, right? So your slope is the change in y over the change in x, and I can't write. It's the change in y over the change in x. So that means if x goes up by 1, then my slope should tell me how much my y will go up. So for 1 month, that's our x changing by 1, we're going to have to pay $44. So what the slope tells us is that the membership is $44 a month. Okay? Now, if I plug in 0 for x, I get y equals 143, which is the y-intercept. What's 0? If I plug in 0 for x, what am I talking about? I'm talking about if there are no months. In other words, before I'm even a member for a month, there's still going to be a cost involved because y is still cost. And so it's $143. So the y-intercept lets me know that there must be a startup fee seriously, of $143. Okay? So that's what that means. All right. Graphing a line. To graph a line using standard form. Like we said before, there's this cover-up method that we can use, and we can find the x and y intercepts. So to find the x-intercept, you cover up the y term, so let y equal 0, in other words, and solve. So you get 3x equals 12, divide by 3, and x is 4. That means on the x-axis, we're going to hit 4. And then for the y-axis, we cover up the x's, or let x be 0, and solve for y. So divide by 4, and y is 3. And so 3 on the y-axis is right here. That's our line. So we draw a line through that the best we can. That's not too bad. And that's graphing a line using standard form, right? That gets us where it hits the x and y axis. Sometimes those intercepts aren't very pretty, so another method would be nice to have, okay? We'll talk about that a little bit later. All right, quick example here. You can rent DVDs at a local store for $4 each. An internet company offers a flat fee of $15 per month for as many rentals as you want. How many DVDs do you need to rent per month to make the online rental a better buy? Okay? All right, so we can rent DVDs at a local store or an internet company. Okay, so let's come up with how much you would have to pay to rent DVDs from each place. So if we let Y be your cost and X be the number of DVDs, right? So let's see. How do we find out the cost for the store rental? Well, it's $4 each, so it must be Y equals 4X. Okay, again, where Y is the cost and X is the number of DVDs. Well, for the internet online rental, they're just going to charge you $15 and let you rent as much as you want, right? So $15 is definitely more than 4. At some point, the number of, if you only rent a movie or two, then you're going to want to get it from the store because you're going to pay less. But at some point, these two are going to be equal, and then the online rental becomes a better buy. So how many DVDs did you have to rent? Well, we could find out where these two have the same cost and go from there, right? And so we can do this, since we're talking about graphing lines and we have some linear equations, we can just graph the lines. Well, Y equals 15 means that our line is going to be horizontal because there is no slope. We go to Y, we go to 15 on the Y-axis and graph this guy straight across. Okay? And then we use slope-intercept form to graph for the store. So our y-intercept is 0, so we come down here. And then the slope is 4, so we go up 1, 2, 3, 4, and, so we go up 4. Sorry, this is scaled. I didn't notice the scale. You should always notice your scale. So we go up 4 over 1, up 4 over 1, and then we can graph our line up here. So that's what you see there. Okay? Now, where they intersect, they're going to have the same x and y values. Y is the cost, so this is where their cost is going to be the same, where they intersect. Okay? So, using this graph, you can see that it's cheaper to rent locally if you rent 3 or fewer, right? 3 being right here. Then this is the store cost. It's going to be better if you rent 3 or fewer. But if you rent 4 or more, then it's going to be cheaper to just use the DVD rental online. Okay? i.e. Netflix, right? All right. Good. So that's a little bit about lines, graphing lines, and how we can use the idea of graphing lines to model some real-world situations. Now, we've got some theorems that have to deal with perpendicular lines. And so let's get to those. Okay? First one, theorem 3.8. Again, the number doesn't matter. If two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. Okay? A linear pair of congruent angles means they have to add to 180. They have to be the same, so they're going to be right angles. So basically it's saying if two lines intersect to form right angles, then the lines are perpendicular. So if angle 1 and angle 2 here are congruent, then G and H are perpendicular. We know that automatically. And I just talked about why. It's sort of our proof, I guess, verbal proof. Now, the next theorem, theorem 3.9, says if two lines are perpendicular, then they intersect to form 4 right angles. So it's kind of what 3.8 says. Just again, what do you know, when do you know it, and what can you conclude because of what you know? And so here we talk about A and B being perpendicular, and if they are, then all these angles, 1, 2, 3, and 4, are going to be right angles. Okay? So, how do we use this idea? In the diagram here, in this first example, line AB and line BC are perpendicular. Remember, this symbol means perpendicular. Okay? What can you conclude about angle 1 and angle 2? Well, if that's the case, then angle 1 and angle 2 are right angles. Okay? No problem, right? If those two lines are perpendicular, then 1 and 2 have to be right angles. They're also going to add to 180, by the way, because they're a linear pair. Anyway, moving on. So I think, again, review about perpendicular lines. Theorem 3.10 says if two sides of two adjacent acute angles, okay, two sides of adjacent acute angles are perpendicular, then the angles have to be complementary. Okay? In other words, in this diagram here, if AB and BC, if line or ray BA and ray BC are perpendicular, then angle 1 and angle 2 are going to be complementary. Automatically, they're going to add to 90. Okay? So we can use these ideas, these theorems, in the idea of a proof. So for example, prove that if two sides of two adjacent acute angles are perpendicular, then the angles are complementary. So we're going to prove this last theorem. Okay? Well, if we're given the fact that ED and EF are perpendicular, those rays, we have to, that's what our theorem says. We're assuming that that's true. We want to prove that 7 and 8 are complementary. Okay? So here are our statements. First one, ray ED is perpendicular to ray EF. Why? Because it's given to us. Well, if that's the case, if these guys are perpendicular, then they do make a right angle. That's from, so angle DEF is a right angle, and that's from theorem 3.9, which I don't need you to remember numbers. Just say perpendicular lines intersect to form 4 right angles. Just paraphrase the theorem. Makes a lot more sense. Now, the measure, so from DEF being a right angle, the measure of angle DEF is 90. How do you know that? Well, you had to know the definition of a right angle, so that's what we're going to use here. Now, since angle DEF is 90 degrees, since the measure is 90 degrees, we know that the measure of angle 7 and the measure of angle 8 have to add to 90 degrees, and that's because of the angle addition postulate. 7 plus 8 has to equal the whole thing, which is 90. Now we do a little bit of substituting here. We take 90, still on my highlighter here, we take 90 and we substitute it in for angle DEF, and so we're using the substitution property to say that the measure of angle 7 plus the measure of angle 8 equals 90 degrees. Now, from here, we know that if 7 and 8 have to add to 90, that makes them complementary, and the reason is because we had to know the definition of complementary angles, and so that's what we're going to use for our reason here. Okay? So using some of these proofs, or some of these theorems to help us write our proofs. Okay? All right, so more dealing with, going back to what we're talking about in this chapter, parallel lines and transversal. So theorem 3.11, the perpendicular transversal theorem, says that if a transversal is perpendicular to one of two parallel lines, then it's perpendicular to the other. In other words, if line H and K are parallel, and J is perpendicular to one of them, then we can automatically conclude that J is going to be perpendicular to the other one. So J is going to be perpendicular to K. Okay? Now, sort of working backwards in theorem 3.12, the lines perpendicular to a transversal theorem says that in a plane, if two lines are perpendicular to the same line, then they have to be parallel to each other. So now, instead of talking about the lines being parallel and knowing that the transversal being perpendicular to one, it has to be perpendicular to the other, then we talk about if if line M and line P are perpendicular and line N and line P are perpendicular. So if M and N are perpendicular to the same line P, then those two lines have to be parallel. They have to be. There's no other explanation. So that's the conclusion we're going to make. Again, it's all about what you know and when you know it and what you get to conclude because of what you know. Okay? So some examples. Determine which lines, if any, must be parallel. Okay, so you look at this diagram. Okay? And it looks like if S is a transversal, P and Q are both perpendicular to S, so they're going to be parallel. We also see that S and T are both perpendicular to Q, so S and T must be parallel. Okay, so in here, P must be, P must be parallel to Q. Okay, because they're both perpendicular to S, and S must be parallel to T because they're both perpendicular to Q. Now next, is B parallel to A, and is B perpendicular to C? Is B parallel to A? Yes, because they're both perpendicular to the same line. Is B perpendicular to C? Well, since A and B are parallel, now that we know that A and B are parallel, and A is perpendicular to C, then that means B has to be perpendicular to C. So yes. Even though it's not marked in the picture, we know that that's got to be true.